Susie. Well, we've known since the very earliest days of quantum mechanics that quantum properties are profoundly influenced by topology. I'm not sure what people think of as the first example in this context, but since we have Dirac at the back looking down on us all, I would say the first example I know of is Dirac's work in the early 1930s on the magnetic monopole, where he developed arguments, purely topological arguments, which led to rather profound conclusions, in that case that the existence of a single magnetic monopole would force all electrons to have the same charge. A very profound and exciting piece of work. So what I'm going to be doing is discussing the influence of topology on quantum mechanics in the case of quantum graphs, where of course we have in graphs the opportunity to develop spaces with arbitrarily complicated topology. So the issue will be how that topology influences the quantum properties. And this is joint work with my colleagues Jonathan Harrison and Jonathan Robbins. And since I too am a Jonathan, if there are any other Jonathans in the audience, you're welcome to join the collaboration. Otherwise, find someone else to work with. So we'll be talking about this, and the issue will be, as Uzi indicated, to try to take the first steps towards understanding properties of quantum graphs where there's more than one quantum particle present. So quantum mechanics of single particles is a very, very well developed subject. Of course, there are still surprises and many interesting features that one discovers, but by and large we have a good intuition for that. Even in the simplest examples, quantum mechanics of very large numbers of interacting particles is still extraordinarily difficult, and there's still profound issues that are not understood there. And it's my view that a direction of research that I believe would be very profitable would be to start, in the case of quantum graphs, to move in that direction, to start thinking about quantum graphs with many interacting quantum particles on them, to see whether that gives any insight into these very difficult and challenging problems in condensed matter physics. So this will be an attempt to take a very first, very faltering step in that direction, and Jens Bolter will speak afterwards on work along the same lines. So as I say, this talk will tie together two themes. One is what happens on quantum graphs when you have more than one particle present, and the second will be influence of topology. And I'll be drawing these two themes together. But before I get to quantum graphs, let me just sort of remind you of some background material, undergraduate background material, I suspect for most of you, about issues relating to topology and many particle quantum mechanics. So let me start with the simplest example. This is one particle in d dimensions, and there we understand quantum mechanics relatively well. We have a wave function, for example, depending on position, and we know that we can change the phase of the wave function via a gauge transformation. And the price you pay is to change the momentum operator from the usual gradient you add on the gradient of the phase phi, so that you go from a simple derivative to a covariant derivative, or you add on a connection if you like. And in the absence of magnetic fields, this connection has zero curvature, so as is well known, you can write the phase phi as the line integral of some vector potential A where A has zero curl. Now topology comes in if you start asking about one particle in a space where you exclude a point. So for example, if we exclude the origin from this space, you can ask how that influences the quantum mechanics. And the answer is that in dimensions d greater than or equal to 3, this has very little influence. And you see that pretty directly from the Feynman path integral approach to quantum mechanics, that most paths don't pass through this point and don't really notice it very much, not much influenced by it. But in d equals 2, you do have a profound influence when you exclude a point. And if you take the Feynman path integral viewpoint, you see that immediately, because in R2, if you exclude the origin, you go from a space that's simply connected to a space that's multiply connected. And so paths in the path integral can be characterized by their winding numbers around the excluded point, and these form separate classes which can't be deformed into each other. So in the path integral, in the sum over paths, you get a term which is kinematically possible, can't be excluded on any kinematic grounds, where you have an arbitrary phase multiplied by the winding number of the paths around the excluded point. And you can think of these phases as corresponding to one-dimensional representations of the group that describes the topology of this space, the fundamental group. In usual Schrödinger quantum mechanics, this of course comes about because in the space Rd minus 0, where we've excluded the origin, all of what I said here holds, but at 0, it can be the case that curl A can be non-zero, because that point lies outside the space. So this means that under gauge transformations, you have a curvature, you have a connection which has zero curvature, but may still have holonomy. And this holonomy generates representations of the fundamental group, just as in the Feynman picture. So the kind of well-known idea is that in multiply connected spaces, topology plays a key role. It plays a role because of the phase factor that's allowed here kinematically, that comes through representations of the fundamental group of the space. Now, of course, this isn't just kinematics, because you really do see this in quantum mechanics, and this is the origin of the Aharonov-Bohm effect. And you see this if you actually allow a magnetic flux line to thread this point. So you do experiments on this, and this effect was discovered just over 50 years ago, 1959, and it's a very profound effect in quantum mechanics. So you really see the influence of topology in the Aharonov-Bohm effect. Now there's another place that you see the influence of topology in textbook quantum mechanics, and this is where you have two particles. In Rd, and again, no magnetic field. So if we have two particles, we have a wave function which depends on the two positions. And if we assume that these particles are identical, then we can ask the question of what happens if we interchange the positions. So how do we transform the wave function under exchange of the positions of the particles. And this, of course, is well known. This is one of the foundational results in quantum mechanics, that the wave function transforms in a simple way. If I rephrase this slightly by looking at relative coordinates, x is x1 minus x2, the question is how psi of x is related to psi of minus x, and we know that what appears in the question mark is either plus or minus 1, depending on whether you have fermions or bosons. So there are two possible choices of transformation, either the wave function symmetric or antisymmetric under interchange of the particles. It's symmetric for bosons and antisymmetric for fermions. And the spin statistics theorem then relates that sign to the spin of the particles. That's a separate issue. Kinematically, these are the possibilities. And this, of course, is responsible for some of the most profound consequences of quantum mechanics. Differences between fermions and bosons really underpin our understanding of electrical conductivity, of the structure of matter. Now, what's perhaps less well known, but has been known for about 30 years now, is that this is the case only in dimensions d greater than or equal to 3. So in 2 dimensions, one can have a different story. In 2 dimensions, this question mark can be any phase factor. So here we have fermions and bosons, and in 2 dimensions you can have a different type of behavior, and these are called anyons. Essentially because you can have any phase factor. Now the origin of this, it turns out, is exactly the same as the explanation of the Aharonov-Bohm effect. So let me explain that briefly. The issue is to think very carefully about precisely how you develop the quantum mechanics of more than one particle. What precisely are you doing? What space are you quantizing? Well, what you're really doing, if you have, say, 2 particles, is the space that you're quantizing is the space in which the 2 particles have their coordinates, have their positions. But one excludes the set of points where the particles are coincident. These are actual particles, they can't both be at the same position, classically. And if these are identical particles, one should factor out the interchange of the particles. That's a symmetry. So this is the space, usually called the configuration space, in which the particles move. And what one has to do is to develop the quantum mechanics on that space. Now the whole issue is that whilst the space in which the 2 particles move might be simply connected, the configuration space may not be simply connected because one's excluding points. I'm talking about classical mechanics here. Yep. So there are points that are excluded in the space, and this may render the space non-simply connected. And we know that in non-simply connected spaces, one can have more interesting behavior. So the idea is that in d greater than or equal to 3, one's excluding a single point. Imagine the relative coordinates. In terms of relative coordinates, so in x space, this actually becomes d minus 0 divided by S2. So in this space of relative coordinates, excluding the center of mass coordinates, one excludes one point, So essentially this has, as we learned from the Aharonov-Bohm effect, no effect on the quantum mechanics, but one has to factor in that positions x and minus x are identified, and when you do that, this gives rise to the fact that there are two possible signs, plus or minus 1, in the interchange of the wave function. Essentially, because if you go around twice, that corresponds to one cycle, and this, because all paths can be deformed and exclude that excluded point, e to the 2I theta is 1. That's the statement that there's no effect, that the excluded point has no effect, but you have to go around twice to see that. So the phase ti theta is plus or minus 1. And this just corresponds to the fact that the fundamental group of the configuration space is S2, and these are the one-dimensional representations of S2. In d equals 2, we're in the plane with an excluded point at the center. So this is exactly the Aharonov-Bohm effect. And so for exactly the same reason, you end up with a general phase factor e to the I theta as a possibility. And these phase factors simply correspond to one-dimensional representations of the fundamental group in this case, which is just the braid group, B2. So we have these as possibilities. Now what's striking is that in this case you get a phase factor without the need for any external magnetic field. To see the Aharonov-Bohm effect, you actually have to put a magnetic field in by hand. For these anyons, you see this phase factor without any external field at all. This comes from the singular and remarkable properties of many particle quantum mechanics. So this phase, to see these kind of Aharonov-Bohm phases or gauge phases for one particle, you need an external field. Really external, it's actually external to the space in which the particles move. But for the anyons, this comes from the fact you've got two particles quantum mechanically interacting, and so you get a phase factor without the need for any external gauge field. Now these anyons are tremendously interesting. They underpin some very remarkable physics in 2 dimensions. So of course you don't see fundamental particles that are anyons, because we don't know of any fundamental particles that are constrained to 2 dimensions. But you do see these in collective excitations of many interacting particles. So if you have many interacting electrons constrained to lie in a 2-dimensional film, the excitations of those electrons can be anyons. That is, they can be like particle-like excitations which under interchange have a general phase factor. And this behavior, this anyonic behavior, is responsible for the very remarkable physics which is now rather well known of things like the quantum Hall effect. The fractional quantum Hall effect is, to the extent that it's explained by the fact that excitations of electrons in 2 dimensions can be anyons, not just fermions and bosons. Okay, so that's the background. Now the question is, I've explained to you that the topology of the space that particles move in can have a profound influence on the phases one gets when one interchanges particles. It explains why in dimensions 3 and higher you only have fermions and bosons. It explains that in 2 dimensions you can have a more general class of behavior, that's sort of anyonic behavior. The question now is what happens if we look at spaces which are intrinsically interesting topologically, for example at quantum graphs. So the idea is to look at graphs with interesting topology, put more than one particle on, and see how the topology of the graph influences the phases one gets under interchange of the particles. So what I'm going to do is show you how the problem's set up, discuss the kind of spaces one gets with more than one particle on a graph, and then give you a few examples. But I won't try and give you the general picture because I'm not sure there's time. But I hope from the examples I give, you'll get a feel for what's happening here. So we have our graph. For example, it's called the graph G, and this will be described by some adjacency matrix. And I'm going to think of this as not as a metric graph, could do, but the problem, it turns out, is somewhat, well, quite significantly simpler if we think of this as a discrete or combinatorial graph. So we simply have points with connections between the points, and we'll think of this as a particle at these points jumping between the vertices of the graph discretely. So the quantum mechanics on here will simply be, the Hamiltonian will simply be the discrete Laplacian. Acting on the graph in the usual way. So essentially, up to a shift determined by the valency, it'll simply the Hamiltonian will simply be the adjacency matrix of the graph. So this is the one particle structure. This is one particle on the graph. Quantum mechanically is described by the one particle Laplacian, if you like, the usual discrete Laplacian acting on the graph G that the particle is constrained to sit on. The question now is, what happens if we put more than one particle on the graph? How should we think of this as a space to quantize? Well, it's already indicated for us what we should do. If we have two particles, we should look at the configuration space for those particles, exactly as I did in the examples I gave earlier. So for two particles, the configuration space for the graph G will simply be the Cartesian product of G with itself with coincident points excluded, and if these are identical particles, with interchange factored out. So these are again two identical particles. So what do these kind of graphs look like? So we start with our favorite graph. We have two particles on it. What does the configuration space look like? Let me give you some examples. If the graph is a ring, we're to think of putting two particles on this graph. So the labels, we'll get a new graph, which is the configuration space. So this is G. C2 of G will be labeled by a pair of positions where the two particles can sit. But since we're factoring out interchange of the particles, and since we're subtracting points where the particles are at the same vertex, which we imagine the two indices as different, and for example, the first index always being greater than the second index. So in this case, we can have particles at 1, 2, 1, 3, and 2, 3. And these are connected to each other because I can go from 1, 2 to 1, 3 in one step, and I can go from 1, 3 to 2, 3 in one step. So the configuration space is just the same as the original graph. So not terribly exciting. But as soon as you go to a slightly more interesting graph, you do get much more interesting behavior. So let's take the star graph. So if we call this 1, 2, 3, 4, we can have particles at 1 and 2. We can go from that configuration to particles at 2 and 3. From 2, 3, we can go to 1, 3. From 1, 3, we can go to 3, 4. From 3, 4, we can go to, oh good heavens, have I messed this up? 3, 4, we can go to 1, 4, yep. And from 1, 4, we can go to 2, 4. And from 2, 4, we can go back to 1, 2. So the configuration space now, whilst the original graph has no loops at all, no way to thread this with a magnetic flux line, as soon as you have two particles on the graph, there's now a non-trivial cycle. So there's the possibility when you quantize of having a phase factor which corresponds to going round the configuration, this cycle in the configuration space. So even for this sort of humble star graph, you can have anyons, and these anyons correspond to the phase you accumulate by interchanging the particles going round this cycle here. So there's one anyonic phase. So without the need for any external magnetic field, already for two particles on a star graph, you can have one anyonic phase. I'll leave it as an exercise to show that if you have a star graph two, 3, 4, 5, 6. On n with n vertices, you can have actually more than one anyonic phase. You can actually have the number of anyonic phases is a half n minus 2 times n minus 3 anyonic phases. So rather unusually and completely differently to quantum mechanics of many particles in a plane, where you can only have one possible anyonic phase factor, on graphs, on these discrete structures, you can have multiple anyonic phases coexisting. So this is something you don't see in 2 dimensions. It suggests that there's a possibility of new physics on graphs that you don't see in 2 dimensions or integer number of dimensions in usual Euclidean space. Associated with the fact you can have more than one phase factor under interchange. So the phase factor you get depends on precisely how you interchange and comes about through the non-trivial topology of the configuration space. Sorry? Nope. Sorry? I hope there will be. This is a prediction that comes out of this sort of analysis. Now another example, which is sort of intermediate between the two, and which shows that as soon as you go to even slightly non-trivial graphs, you get very rich structure, would be what my colleague from Texas calls the lasso graph. 1, 2, 3, 4. So this has a star graph component as well as a cycle. So if you imagine one particle on here, you could have a phase factor of Aronoff-Bohm type. That particle would simply be going around this loop, and you could thread this loop physically with a flux line through there. What about if you have two particles on the graph? What's the configuration space? So we have two particles here. We can have particles at 1, 2, 1, 3, 2, 3, 4. Let me try and remember. 1, 4. I can have them at 2, 3. 2, 4. Sorry, let me get this right. I've got 1, 2, 1, 3. I can go from 1, 2 to 1, 4. That's right. 1, 4. I can go to 2, 4. 1, 4 is not there. 1, 3. I can go 1, 3. I can go to 2, 3. And these connect together. 2, 3, 4. So I can go from 1, 4 to 1, 3. And I can go from 2, 4 to 2, 3. So the configuration space in this case has 3 separate potential cycles that one can have. So one of these cycles corresponds to one particle sitting at position 1 and the other particle going around the cycle 2, 3, 4, 2, 3, 4. One particle fixed here and the other particle going round this loop. And that corresponds to an Aronoff-Bohm phase. So that's not an exchange phase. One particle stationary, the other particle simply going round the loop, which you can physically thread with an Aronoff-Bohm phase. The other loop, however, corresponds to a particle going from 2, 4, 2, 4, 2, 3, 3, 4, 2, 4, 2, 3, etc., going around like that. That's a genuine exchange phase. So on this graph, you can have Aronoff-Bohm phases and exchange phases coexisting. So this is an example where you start to see that on these graphs you can have immediately a very simple graph can give rise to very complicated configuration space when you have more than one particle on. So so what I hope these examples illustrate is that you can have these general phase factors, and these of course just correspond to representations of the fundamental group of these spaces. These spaces have immediately non-trivial topology, and one can set up a discrete analog of the fundamental group, and these allowed phases are just the one-dimensional representations of that. Now, if you have more than 2 particles on, you see very quickly this will get really very complicated. Yeah.
I don't have any of the physics background, but if I have one particle just going back and forth on the 1, 2 spots and the other one on the 3, 4 spots,
yeah,
I can build a non-trivial cycle.
That's right.
So it seems like particles don't know anything about each other.
That's a very good question. I was going to come back to that a little later, but let me answer it now. No, it's a very good question. So, kinematically, if you're restricted to this discrete space, you could have that, and that's kinematically possible. But it seems on physical grounds something you might wish to exclude. So that corresponds to going around this central cycle here. I was going to come back to this in general, that the question is, what do you want to do with this game? This could be a game in pure mathematics, in which case, yes, you would have to allow a phase factor there. But if you imagine these graphs as arising as some limit of a metric graph, so if you imagine this is a metric graph where the particles are largely constrained to lie at these points, but do actually have to travel between them physically, you would want to exclude that as a possibility. It would seem to be an exchange which you might want to exclude on physical grounds because it comes from something which, as you say, if you imagine this as being continuous, then simply going backwards and forwards between these 2 points and those 2 points, that doesn't correspond to a genuine exchange. Whether that's in or out of the game is a matter of what you want to achieve. So our view is that if we're trying to model physics, that on that ground we should try to set these phases to be 0. But that's sort of additional, it's not a part of the mathematical framework. That's something that comes from saying, this is the physics we want to model. We believe that these kinds of phases should be excluded. But you're still left with two phases here corresponding to this cycle and this cycle. So if you have more than two particles on these graphs, it can get rapidly extraordinarily complicated. And you then have the possibility for something rather interesting, which is more than two particles. You can immediately get not just phase factors appearing, one-dimensional representations of the fundamental group, but unitary matrices appearing, describing the transformations under exchange. And these correspond to what are called, in physics, non-abelian exchange phases, or non-abelian anyons. And these are things which people have spoken about. My understanding, I'm not an expert on the field, is that these are theoretical possibilities people have explored, but where they haven't found yet any experiment to support the existence of non-abelian anyons. So it's interesting to speculate whether these kinds of simpler topologies would give ways to see the effect of non-abelian anyons, but we haven't formed a fixed view on that yet. There are some rather more interesting things that also appear. So when you go to slightly larger graphs, if we look at the graph, K6, which is the graph like that. Now I won't try and write down the graph that corresponds to the two-particle configuration space, but this is the first example where you find a phenomenon which we find rather interesting, which is that some of the exchange phases, in all these earlier examples, the exchange phases can be general phase factors. In this example, and we have some other examples, some of the exchange phases are allowed to be general phase factors, and others turn out to be discrete phase factors. In this case, they correspond to signs, plus or minus 1. So it seems that when one gets to more complicated, yes?
How many vertices is that graph supposed to have?
This graph has...
Is it 5 or 10?
It's 5. 5.
So the interior crossings are...
Yes, yeah. They are crossing.
That's right.
Yeah.
It's got 5 vertices, so it's called K6.
Yeah, of course they say.
You're written K6.
Oh, sorry. Yeah. Yeah, I lost my train of thought. Oh yeah. On this case, you can have more complicated anyonic structures, where the phases are allowed to be not just sort of any old phase, but can be discretized. And that seems to be something which also doesn't appear in the examples people have considered elsewhere for anyons. So it seems that these graphs do give an opportunity to explore structures which, because of their very non-trivial topology, are perhaps opportunities to see behavior that hasn't been seen so far. Now, where might one see this? Well, this is really rather speculative, but I think it's worth speculating here. Graphs, of course, were introduced a long time ago as models of molecules. So we might imagine these as physical molecules with and the discrete dynamics corresponding to an electron hopping between sites on the molecule. So far, people have done experiments where they've seen anyonic behavior on samples corresponding to electrons moving in a plane, or very simple geometries like that. I think it'd be rather interesting to speculate what would happen if one tried to do experiments corresponding to looking at electrical conductivity, potentially in the presence of a magnetic field where one had either a network of quantum wires or where the wires that one had were themselves topologically non-trivial. For example, the wires themselves might be molecules. So one might speculate that there one would see conductivity, one would see electrical conductivity that was influenced by the fact that one can have excitations which can be not just the usual anyons where there's one anyon phase, but where one can have multiple anyons, and where some of these anyon phases could be discrete. Let's say that's rather speculative. There's something rather definite that I think we are very interested to pursue, and this is the situation where one has more than two particles. As I've indicated, one can write down some simple examples for how one can generate these configuration spaces. But the issue then of determining the fundamental group of the configuration space is enormously complicated. There is, however, a machinery which spits out at least the one-dimensional representations of the fundamental group, and this is an area that with mathematics called discrete Morse theory, where we see some potential for maybe developing a general framework to describe some of the structures which I've given you some examples for here. So is this connected with physics? Not a clue. It smells like it might be, but we don't know at this stage, and it would be very interesting to pursue that. But it does seem that at least as regards extending quantum graphs into the realm of having more than one particle, this shows that one can expect very rich behavior associated with the sort of topological structures underpinning the graphs. That's it.
Yes, please, Daniel.
Yeah, you mentioned the fractional quantum Hall effect. Now, I forget what fraction is that to be a non-abelian. There's a theory explaining it. Experimentally, there were some experiments being done. I know there's a
Yes.
theory that can explain it using abelian theory. A theory can explain it using non-abelian.
Yes.
Have the experiments?
No, the experiments. The experiments are still very controversial. Some groups say they've seen the influence of non-abelian anyons, and other groups have not reproduced those results. Is my understanding of the field, but I'm really not an expert on that. But that's it seems to change with every issue of physics today that comes out as to whether this has been seen or not yet.
Any further questions? Maybe, please.
Are you including spinning?
No. So far, this we've not included the effects of spin, the sort of spinning particles having spin, and that would be very interesting to do. Of course, if one goes to non-abelian phases, one wants to think of these wave functions as vector valued, and there presumably one would wish to include spin as a variable.
May I ask a question? What happens if you apply this to a lattice? You get what? Is there any new statistic? Because that is
No.
a check on the
Yes.
correspondence with the R2, let us say.
That's right. No, for a lattice, you don't get any. The phases that one gets are all the phases one would wish to exclude on physical grounds.
So you don't. There is no contradiction with what
No.
you. Or
No.
It agrees with R2.
It agrees with R2.
Then if
Yeah.
you take another, not a square ladder, but a hexadecanal.
Yeah, it's at least the examples we've checked, and I'm not sure we've been exhaustive in this. All of them have the same continuum limit, which is the usual R2 behavior.
But there is always one question that chemists ask: what happens if you change the solvent? So the physicist asks what happens when you add the interactions.
So far this is pure kinematics. So one could potentially one's not
So then the
excluding.
potential will be like a local potential.
Yes.
Of this,
Absolutely, yeah.
Okay. Anyone more questions?
Oh, actually,
Yes, please.
I was confused by answer to this question. So if you have a square lattice, surely, and then generate this two particles, this graph, surely there are lots of cycles.
There are lots of cycles, but they're all of the type where one would wish to exclude on physical grounds. So particles moving around, looking like they've interchanged, but not actually having done so.
Yes, please.
Have you tried a asymptotical approach to this one?
Yes, and it leads to exactly the same.
Yes.
Yeah, fits exactly the same picture. Yeah.
Well, let's thank John for the nice.